So in this video, we're going to look at resolving some indefinite integrals when we have rational function integrands. So remember, rational functions are just ratios of polynomials. So in this case, I have a very simple rational function, 4 over 3x to the fifth. So I'm going to rewrite the integral. So I want to integrate 4 over 3x to the fifth dx. We're going to do two examples, a simple example and then a little bit more complicated one. So in this case, what we want to recognize is that this can be rewritten as 4/3. It's really times 1 over x to the fifth dx, which is the same as 4/3 x to the negative fifth. So if we want to bring, x to the negative fifth dx. So if we want to bring the base x into the numerator position, which we do want to do, we're going to need to change the sign on that exponent. And then I want to recognize that I have a constant multiple of a function or an expression, so I can factor the constant multiple out of the integral sign, which would leave me 4/3 x to the negative fifth dx. And then you focus in on this term. Once I have it down to a variable expression, I want to look at this and say, well, how would I differentiate that? Well, I would use the power rule, and I would subtract 1 from the exponent. But because we're working backwards and integrating or anti-differentiating, we're going to need to add 1 to the exponent instead of subtracting 1 from it. So the antiderivative is going to be 4/3 times, it's going to be x to the, we need to add 1 to the exponent, so it's going to be negative 5 plus 1 is negative 4. The exponent gets 1 bigger. But if you differentiate d dx, x to the negative fourth, you get negative 4 times x. Negative 4 minus 1 is negative 5. You don't get x to the negative fifth. And your check on work is to differentiate. So x to the negative fourth, when we take the derivative, we get negative 4x to the negative fifth. So this part's correct. So we've got to make a tweak or an adjustment right here to get rid of this negative 4 when we differentiate. So the tweak is going to be to multiply by the reciprocal of negative 4, which is just negative 1/4. So if we differentiate d dx of negative 1/4 x to the negative 4, we would get the negative 1/4 times the exponent would come down times x to the decrease the exponent by 1. Negative 4 minus 1 is negative 5, and negative 1/4 times negative 4 equals 1 times x to the negative fifth, or just x to the negative fifth. So there's the check on work. We've got that little tweak factor in there. Now we need to add on plus our constant of integration. And then to simplify things a little bit here, we see that 4 divided by 4 equals 1, and 1 times negative 1 is just negative 1 over the denominator of 3, x to the negative fourth plus c. And again, we need that plus c because if we differentiate d dx of the negative 1/3 x to the negative fourth plus c, when we take the derivative of the c, we get a 0. So there's infinitely many antiderivatives. We don't know which one is needed, so we put that constant of integration on. So here's another example. We have the integrand, 3x to the fifth plus 5 over 2x squared, is a rational function because it has a 5th degree polynomial in the numerator and a 2nd degree polynomial in the denominator. So I'm going to go ahead and rewrite my integral. So it's the integral 3x to the fifth plus 5 over 2x squared. And similar to a previous video, the strategy here is going to be to break this up into two separate rational functions. So I can do the 3x to the fifth over the entire common denominator. So 3x to the fifth over all of the common denominator plus the other term 5 over the common denominator, and that's dx. And then I look at the first term, I see that I can simplify it. This is really just 3/2 x cubed, because we get x to the fifth minus 2. We subtract exponents when the base is in the denominator. And here I want to bring that x into the numerator position. I want to bring the base into the numerator position. So when we do that, we change the sign on the exponent. And now I want to recognize that I have the integral of the sum of two functions. So I'm going to break it into individual integrals. So the integral, we have 5 halves x to the negative 2 dx. And then I recognize I have a constant multiple of a function, so the constant multiple can be factored out of the integration process, plus a constant multiple times a function. The constant multiple can be factored out of the integration process. And now we're ready to integrate. We're going to integrate x cubed. So we're going to increase that exponent by 1. So we're going to get x to the 4th. But if you were to differentiate to check your work, you would get 4x cubed. So we need to multiply by the reciprocal of that exponent so that when we differentiate, they cancel. We do get plus a constant of integration, and we're going to get a constant of integration from this integral, but we'll add those two constants into a single constant c. So we'll wait until we're done integrating both terms to add on that single constant of integration. So here I'm going to get my constant multiple times the antiderivative or an antiderivative of x to the negative 2. So for this one, I'm going to increase the exponent by 1. So negative 2 plus 1 is negative 1. And then we're going to need to multiply by the reciprocal of negative 1 is just negative 1. So when we differentiate, the negative 1 times negative 1 becomes a positive 1. Multiplied by 5 halves gives us our 5 halves back here. And we go plus a constant of integration. And then we want to simplify if we can. So we have 3 halves times a quarter is 3/8. X to the 4th. We have negative 1 times 5 halves will be minus 5 halves times x to the negative 1 plus c. And this is good here. If you felt compelled to, you could rewrite this as 3/8 x to the 4th minus 5 over 2 times. We could move that base x back down into the denominator by making the exponent the opposite of what it currently is. So currently it's a negative 1. We could make it a positive 1. We don't need to write x to the positive 1 to get just an x plus c. So again, we could rewrite it with positive exponents only, but there's no particular reason for doing that at this time. So it's okay to leave it with a negative exponent result.